Well, maybe we don't know
Recording is on.
that. So why bother? I guess we all know threading is really difficult to get right. And so, well, I mean, obviously there's some performance benefits if you get it right. But also it seems a shame to waste so much hardware lying around there. So as you can see, 50% have more than 8 threads. About 75% have 6 or more threads. Greater or equal to 8 threads. But either way, there's a lot of hardware resource sitting around there on your device, and if you're not using it, and ultimately most computers aren't being used actively most of the time, unless they're compiling, LibreOffice, I guess. But it just seems like a waste. So we can get there quicker and get answers quicker if we use threads, arguably. And if the work happens to be nicely parallelizable, which not all work is. So we use lots of threads. For LibreOffice, I'm starting with the LibreOffice pieces here, and then we'll move on to col.la, which is slightly different. So we have, one big main thread that does almost everything, almost all of the time. Yes. So we have broadly 1 plus epsilon threading for most cases. Like we have lots of threads, but we're not actually using them for much. So we have pipe IPC thread, which is, I think, probably an artifact of blocking I/O. So if you look at LibreOffice API surface as a whole, almost all of the APIs are blocking. Well, what does that mean? That means that if you do something, it takes a potentially unbounded time until it comes back and is done. So you can imagine, for example, if you're reading from a file, and that file is a remote file on a distant server, and the server is turned off, that it could take a very long time to actually get the data. And so that's a problem. So all of our APIs are currently in the form that things could take a while. And so if we get used to the idea that something tends to take a while, what we often do is then we push it off into another thread. So the thread can sit there blocking, and the rest of the app can get on doing something. So that's one way of doing it, and it's very different to how col.la Online does it. col.la Online is fundamentally about async I/O. We can talk about that in a bit. So the pipe IPC thread basically is just sitting there waiting for someone to connect and talk this remote protocol down a pipe. So you can use that to automate LibreOffice, but I think you can also use it for a factory process, so that as multiple arguments are sent or multiple times the program is launched, those parameters go down this magic pipe that sits in temp OSL underscore something or other. And so instead of that creating a new window, it just a new application rather. Well, it does very transiently create a new application, but then that goes to the existing LibreOffice and reuses all of that bootstrap stuff. So there's a thread sitting there doing that. There's a thread called the config manager writer, which I think is a classical example of underused thread. The config manager, well, so writing is an asynchronous operation typically anyway. Unless the system's under extreme stress, you can write a file thousands of times and it's totally non-blocking. Whether it actually reaches the disk is another question. It's possible that we was put this in a thread because at the end, ideally, you do an atomic change on your file system that sort of syncs and flushes your configuration, so it's never corruptible in between. And so typically you do an fsync on the file. Problem is file systems for most of their history have been so bad that calling fsync on a single file essentially blocked the whole system for every process and flushed all of the data back. Causing amazing latency and and interactivity problems. So it's not clear that doing that in a thread would actually really help much. But anyway, it is what it is. And then we have a thing called self-helper time. I don't know if I've got a slide on this. Maybe I have. Yeah, okay. Well, we'll talk about that in a second. If you git grep for this get shared optimal pool, you'll find all of the interesting places where we're actually doing threading to try and speed up stuff. So the shared optimal pool, I mean, a thread pool is a pretty simple idea. It's primarily there to reduce thread creation and destruction, which was previously thought to be quite a slow thing. As in, if you create a thread, the kernel has to do something and schedule something and. Turns out it's actually blindingly fast to do that. So Whether we really need thread pools per se is not totally clear to me in this modern world. But either way, it's there, and probably some operating system still struggles to do this. So, but the pool then has a whole load of threads ready and waiting to go, and often you'll see that in your backtrace that there's 4, 8, whatever, one per CPU thread often, just ready for work to pop in. And we use that for all sorts of things, and perhaps we'll come to that in a bit. But you'll see all of those threads around. And then, of course, on Linux, you have a whole load of random other threads. At least, there's the glib main thread, dconf workers, gdbus connections, and all sorts of other things. If you switch to Windows, everything gets worse. There's a whole load of, quotes, real-time timer threads, and I don't know quite why they're as necessary as they are, sitting around waiting, not doing much. Yeah, it's not entirely clear what they're, well, I'm sure you can read the documentation on why they're needed. But there's quite a number of those. And also GDI works in a slightly odd way. So the graphics, the way we talk to Windows graphics subsystem is pretty funky in Windows. So I think at some point it was decided it would be ideal if Windows applications had one thread per window, so like top level window. And so I think a lot of things are optimized for essentially creating a new thread for that window and then creating resources inside that thread and rendering with those resources and so on. And this doesn't necessarily fit our threading model terribly well. In fact, LibreOffice's threading model doesn't really fit anything terribly well anymore. So there's a number of ways that things need to be synchronized across threads in Windows that are particularly unpleasant. And if you look at the implementation at the back end, you'll see stuff that makes your hair stand on end. So, some methods can be used in some threads. So, for example, you can draw on a device output from any thread in Windows, but I think you can't create it from any thread. You have to push messages across to other threads to achieve that if you're not in the quotes main thread. Anyway, it's all very complicated and probably worth ignoring. If you're doing something like that, you're probably doing something wrong. And all of this typically results, I guess, apart from the thread pool as shared optimal pool, in essentially zero concurrency. So, there's still pretty much just one thing going on at once, which is great. I'll talk about the timing thread here. So, of course, in the VCL main loop, we have a VCL timer, and you can add that to your main loop, and it will fire after a certain time, assuming that the main thread is not doing anything. So we have this idle thing, we have timers, we try and prioritize those to get things in sensible orders and get events to happen in orders. But this relies on the main loop spinning. And back to here again, pretty much everything is happening in that VCL main thread. So for example, if you're doing a file import and you want to update the status bar, the progress bar, every, say 50 milliseconds, you might think, well, I can just add a VCL timer and update the status bar every 50 milliseconds. Fine, an auto timer that comes every. The problem with that is that because you're doing all of the work in the main thread, the main loop never spins. So you actually never get back to that main loop if you're not very careful. So actually you need to do something much worse than that. You need to work out if it's 50 milliseconds later, and then you need to actually spin the main loop to have a chance of being able to render stuff. This adds all kinds of horrifying reentrancy hazards, which are really, really dire and unpleasant and not good for your health, but broadly works. And so at various times we've had code, I think, that just effectively nails the progress bar onto the screen with some really low-level immediate rendering. That's no longer really possible in the modern world. So we spin and we take reentrancy hazards there as we load stuff, even in a single thread. Perhaps you're thinking, what is a reentrancy hazard? You probably ought to think, what is a reentrancy hazard? So reentrancy is essentially when you're getting, your method is called again from some code path you're not expecting. So what does not expecting mean? So for example, when you're loading a file, it might be nice if the code sort of flow all completes in a sensible way before it's done. So for example, if you're loading a file, maybe you have a partial document that's half constructed in memory and you've registered all sorts of things in various different places. And now you call this main loop function to render your progress bar. while that's calling, something like a VCL timer that's not your timer, but someone else's timer could get run. And that timer could do all sorts of things. It could be a macro or something like this that comes in and says, hey, tell me all of the documents I've got and what all of their titles are, and then starts to manipulate them. And of course, at this point, you've got a half-constructed document, partly set up, perhaps findable in various places that it shouldn't be found. And this is a very typical reentrancy hazard, that you would assume that your code runs to completion and nothing weird happens during that. And I guess we assume this all the time. We type new object type, new foo class, and we tend to assume that during the new foo class, we won't ourselves get called again by some callback or mechanism that intermittently comes in. But anyway, so even in single-threaded programs, you can have these rather unpleasant reentrancy hazards. But of course, we're most familiar with that from the threaded environment, perhaps, where several people are calling the same method at once, and then the solution is a mutex. But in a reentrancy environment, it's not really easy to solve that way. Anyway, so why do we have a whole thread for timing? Well, simply because we don't have this main loop running. The initial approach was simply to call give me the time of day, and so you can call get time of day, and you can do that. I think we did that in the central inner loop where we're loading cells, because spreadsheets tend to be the ones that have the most data, and turns out it's really very expensive. If you're in your sort of inner loop, you're calling get time of day. At least in the past, it would do a system call, and so the performance of loading spreadsheets was kind of dominated by checking whether we should update our progress bar, which is unfortunate in the extreme. So actually, in some cases, it sort of makes sense to have another thread running whose whole job is just to wait. So he can wait for 50 milliseconds, and then he can do something cheap and simple, like setting an atomic variable of some kind, or setting some counter somewhere that we can then check very simply to see if we should then actually take action. So yeah, just this, I think, has been partly removed by lots of clever user space time accounting, because plenty of other people see these problems. But then again, cross-platform, how well does that work? Not clear to me. So yes, there you are, a whole thread for not doing much but sleeping. Great. So question is, since we're a threaded application, how can we protect the pieces that need protecting, and how can we tease out pieces and start to use them in a way that actually can use all those 6+ CPU threads, 5+ that you have lying around not doing anything? So if you see, we have essentially one big lock that protects pretty much everything in LibreOffice. So where pretty much is not some of the things on the right here, but yeah, it protects all this lot. So the good news about that is that almost no one needs to care about threading at all. So good for you. That saves lots of hassle and bother and getting it wrong. It does mean that every time that we call into the VCL code, which we call into and then out of and into again, we need to take this magic thing called the solar mutex. So the solar mutex is the one big lock that protects almost all of that stuff. So over time, there's been some sort of realization that we should really be doing more here and using threads, and it's good to do that incrementally. So there's two places where that's really happened. So the first is, if we roll back 25 years, there was a really great white hope that if we rewrote everything using Uno, then everything would be thread safe and wonderful, and we could think about making everything thread safe as we rewrote everything to use these Uno components. And I think it's safe to say that this approach is and was a total failure. So as an example, the config manager was rewritten to the config manager 2, I think, at some point. And as in common with any second system, it was horribly over-engineered. And one of the things was they're making it, massively concurrent. There were locks upon granular locking and all sorts of things. And the net result was, as I recall, it took about 50 lock takes and releases to get a single config key. So as you as you said, give me this configuration setting, it would disappear into this rat's nest of nodes and walk trees and lock hierarchies. And, it was all It was all very clever, but at the end of the day, it also happened to not be thread safe. So if you wrote a little test, and I wrote a little test, 8 threads, hammer on it for a little while, you get the thing to crash, deadlock, and fall in a heap. So not the most impressive result. And of course, there's a performance cost of doing all this locking as well. So one of my relatively early contributions to OpenOffice in the day was removing all of the granular locking from Config Manager and replacing it with what we call a code lock that says, Config Manager is a relatively simple piece of code. But as soon as you enter that code, we take the lock. So a little bit like the Solar Mutex, I guess. And as soon as we're going out of it, or just before we go out of it, we release the lock. And then, in theory, all is well. And this, of course, is a very simple way to deal with domains of code when it comes to threading. So if you look at, for example, the glibc memory allocator, it has a very simple API, malloc and free. Okay, like it's slightly more complicated than that. But underneath the hood, then, you can do all sorts of very clever things. But as long as you're taking a lock or some kind of protection as you go in and as you come out, then you can protect all of your accounting for memory management. So life is good. Config Manager is a little bit like that. You would think it would be simple, but unfortunately, when you set keys, there are a lot of callbacks coming out of it. So one of the problems you have with callbacks is and threading is that, in theory, you can have multiple threads reading and writing from the configuration at the same time. Now, this is a really bad idea, obviously, but we should at least try and think about it. And so in consequence, what you can do then is, you could have 2 or 3 people listening for a config key changing. And as you call out saying, hey, this key has changed, those listeners could be removed interactively. And actually, you think that's not very common, but that's actually quite common in many of these patterns. Often you have a dispose or a this object is being destroyed type listener, and people want to know when objects are being destroyed. And very typically, during those destruction things, there's this kind of mutual embrace of referencing, and you actually do go around and update all of those lists of listeners while that's happening. So, yeah, it's pretty nasty. So typically, reference counting is used to overcome this problem that the list is changing underneath you. And so typically, then we would make a copy of the list of all of the people listening. We would reference those. And the atomic reference count, of course, is then very, very simple, I think, to take. And then we would call all of the listeners, some of which, by the time they're called, would have been made defunct. But the reference count means that that the memory is still live and active. And and we clean up like that. So the great white hope was for components to solve everything. But the problem is, when it came to implementing those components, you basically needed to hold the Solar Mutex. So if you look at, for example, the framework code, which is kind of a wrapper around the SFX or the UI pieces of LibreOffice, like how many top-level windows are there, how many documents are there, all this sort of thing. And there's this API, which is great for scripting. And unfortunately, it's used directly in the code in a number of places as well outside the scope of scripting. But at the end of the day, pretty much everything there takes the Solar Mutex because it needs to talk to VCL widgets. It needs to do sensible stuff there. In addition, there's a whole load of components that simply don't bother doing any locking at all. So I forget which ones are particular offenders here, but it's very often the case that they just didn't get the memo and they don't bother taking any locks, and life is good. And they then go and use VCL Solar Mutex stuff. And that sort of works because the Solar Mutex is a recursive mutex. So it doesn't lock you out. It locks everyone else out, but you can take it as many times as you like redundantly, and life is good. Well, or at least you'll still protect it, which is kind of good. Incidentally, do heckle me in the chat if there's I'm sure some of what I'm saying is not entirely accurate, but we're trying. So then we've pulled sort of other pieces out there. So one particular success story I think here is the fast parser. So there are lots of ways of parallelizing things. So for example, let's take the stuff at the top. Actually, let's go for this graphics stuff first. So in graphics, we have all sorts of problems. Like we want to scale an image, and scaling an image means doing a lot of maths per pixel, typically. Possibly the most pathological thing you can do is take like a 10 megapixel image and then scale it down to like 8 by 8 pixels, something like this. And the reason is then that, we've only got 64 pixels, but we've got to do 10 million pixels worth of work to get the 64 by 64 pixel thing, sort of averaging out or smearing out the information from those to get a good quality interpolated image. So to do that, we have these wonderful bitmap super scale filters and graphic import filters that just recognizes, look, hey, we've got 64 pixels here. For each of those pixels, or some such, each chunk of data, we could use a thread. And so we can then maybe do this 8 ways and do 8 pixels at a time. And each of those can do some large chunk of this source image. And we get a really nice speed up from that. There's bigger cache sizes, there's better locality. So, in theory, these are embarrassingly parallel problems. And we can even get a super linear speed up if we're particularly clever and we use more cache because of that. So this is really good. So basically, we take the problem and we split it into identical subproblems, and we spawn all those threads off, and life is good. So that's a really good way to thread things, and that's kind of one whole category there. The XFast parser does something else, which says, okay, so this problem has several steps. We have a decompress stage when we're loading XML out of zip files. Yes, fair enough, Quickie. Yeah, we should really be using AVX and SSE. So let's go into that a bit more. So there's a thing called SIMD, single instruction multiple data, and that's what all these things are doing. And this is essentially a single thread emits a single assembler instruction, and that instruction happens to do 8 pixels at a time or 256 bytes at a time. It does one operation, operates on all of those. And that's quite an alluring thing to do. It uses a huge amount of width in the CPU pipeline. And it does parallelize things, but on a very, very low level per instruction basis. And that's really a great way to do these graphic filters. But even so, you can do the same very parallel instructions on multiple CPUs and then get even more of a win there. So it's kind of a slightly orthogonal concept. Anyway, back to XFast parser. So here we realize there are multiple steps. We're decompressing stuff out of the zip file, and we're parsing the XML. So that means trying to work out where the chevrons are and the quotes and which bit is which. And then we're tokenizing. So a lot of those attributes and names are well known to us. And what we do is we like to turn them into integers so that we can then do switch statements and various things that make life quicker in our code. So there's a whole, let's try and turn this attribute name, whatever it is, like paragraph class or something, into, integer 3, something like that. So there's a whole chunk of work there. And then there's another chunk of work, which is emitting those events out into the core code. So we can break this up into a pipeline, essentially. I like to talk about pipelining a lot, but so we can do one part of it in one thread, we can throw that over to the next thread, do another part in the next thread, throw that over to the next thread, and so on down the pile. Now, this is important for ODF because ODF uses extremely verbose attribute names. Microsoft, of course, in OpenXML went the exact opposite way and used extremely terse names. So, W colon P is a paragraph or something, depending on the namespaces. And so they have all sorts of clever, hard-coded integer matching things that make parsing quicker. And we basically said, well, let's not bother with any of that. Let's just throw all that work into another thread and life will be good. So that thread does its work. And effectively, it's free for us. As long as we're slower at interpreting those things and consuming them, as long as we're slower than that, we effectively get free parsing of the XML files. So that's a really nice win and a really nice way to use another thread and to push all of that work out into another place. In theory, it's also better for instruction cache usage and branch prediction and lots of the non-linearities that CPUs bring in terms of it's really not great to do a little bit of some work and then emit an event that causes a lot of other work to happen. Just for a modern CPU, it doesn't like it. So yeah, some really big wins there, and no real API change. You can just tease this out of the code and run these custom worker threads at the background and get free wins with very little risk for anyone using that in terms of having to think about threading. So the API user still does what looks like a synchronous request, and it just so happens that it's served, from another thread effectively for free. Now, of course, whenever you have multiple threads and multiple people doing stuff, we have a producer-consumer problem. So say we're very much faster at parsing XML, and we have one of these multi-gigabyte calc spreadsheets, which are not uncommon. Someone fills down lots of data, and they want it all in quickly. But were you to unzip that makes some vast amount of space in memory. And we really need to make sure that we're not blowing up our memory. So we can't essentially keep decompressing at top speed and parsing and tokenizing. We have to stall that. Otherwise, the producer will overtake the consumer and rapidly fill our memory with junk. Well, useful junk that we'll use in a minute. But the process of doing that will, of course, consume all available memory, make us hit swap, and life will not be good. So I think in the fast parser case, we have effectively swing buffers. So we fill a buffer full of data and we throw it across, and then we do another one, and then we block until the consumer has finished doing stuff. So that's all very well. It's obviously good to have big buffers because that's more efficient from a flow perspective, but less efficient from a latency perspective because first you have to fill the big buffer. So so for very small files, I think we don't bother using this multi-threaded thing, but that's perhaps we should have some kind of exponential back off in terms of swing buffer size and then just have one code path. But anyway, for small files, we don't do this in the fast parser. As of now, I think. What's next? So the package stuff here. So another problem we have is that deflate is really, really slow. So deflate, or what we use in zip and also gzip and tar-gz and all these things, is really, really appalling way of compressing anything. Not because it's particularly bad. I mean, I think many of the ideas are quite simple, but it's particularly bad for these parallelized devices, the SIMD stuff that Quickie is talking about. The way the bits are arranged doesn't lend itself to using modern SIMD stuff, which makes it extra slow. So ideally, we'd use something like Z standard, where the bit stream has been arranged to make it work nicely with SIMD. But still, ODF doesn't actually do that yet. So there's some patches coming from Indian friends doing good things there. But it'll be a long time before zip files with Z standard compression are a normal thing. And even then, it makes sense to parallelize this stuff. There's a lot of work there. So sometimes when you're writing files, zip files with ODF or XML, OpenXML in them, there's a whole lot of streams. And what we can do is we can add those to a task queue to compress. So that then does it asynchronously. So very nice. It's like an asynchronous write. You write through, and that thread goes and compresses it in the background. So again, there's some potential for producer-consumer problems here, in as much that you really don't want to write an infinitely large file that would compress to something very small and then hold it in memory. And so for some of those, I think we then have this different thing, which is for very large streams, we have this thread deflator, which essentially compresses a single very large stream in multiple threads. And Lubosch wrote that, I think, some years ago, 2019. That's really good because ODF forces us to have our entire spreadsheet in like one massive content XML file. So, it's already bad, I guess, or already, trouble enough in XLSX to have one XML file per sheet. But having the whole spreadsheet in one file is potentially a bit problematic. Anyway, so this then tries to overcome the obvious performance problems there and the fact that 99% of the content in the file is embedded in one XML file inside the zip. So we can then actually try and use more of those threads to speed it up. So a more fun example then is calc formulae. Obviously, we try then to cut a safe part out of the giant solar mutex mess here in calc. So we cut a very little corner off this thing somehow and say, this is the bit that we're going to thread and we're going to make safe. And obviously, we don't do that without profiling. There is 0 point in adding the risk and complexity of threading without really knowing where your problem is. But anyway, we find somewhere that we think is a safe case. So a long formula group, a whole column full of some complicated formula where this would make sense. we then try and remove all the kind of recursion. So, if we have a cell that depends on another cell that depends on another cell, we have some kind of recursive evaluation, and we really don't want that when we're threading. And we don't want to be writing anything. Ideally, we've flattened all of the data we need before we start calculating, so that we're not touching anything. We're just generating an output we can drop back in the cells. So anyway, we check all of our compute dependencies, and then we do this interpret formula group threading. And we try to, Quaylon's done a whole lot of work on this in recent time to catch some silly gotchas that were really screwing our performance there. There are some things that we still need to have locks on. Then I think the number formatter may be one of them. Some things we can potentially duplicate per thread, so you can look up information that's transient in those threads. And then, of course, we try and ignore anything hard, the volatile formulae. So volatile formulae evaluate differently, or every time they're calculated, they evaluate a different way. Macros, of course, throw you into the basic interpreter, which is not where you want to go in multiple threads at once, and so on and so on. And so we find some really constrained subset that we say, we think this is safe, and then we throw caution to the wind and calculate in massive parallel, which is fun. And so far, so good. There's a different kind of area where we do it. So that's one where we add new locks. We keep the solar mutex held, and we just parallelize these little bits here with a subsidiary lock. There's a more fun example, which is this parallel sheet parsing. So in XLSX, it turns out that we can actually import multiple sheets at once, which is kind of cool. And the problem is that there's quite a lot of complexity in importing a spreadsheet. We could have an embedded OLE object with a word processing document in it, for example. And that's a bit of a problem. You can't really make all of that thread safe at once. So, and we know the lock that protects all of that stuff is the solar mutex. So we've got to have the solar mutex held in every thread that's doing anything non-trivial. Of course, the center of the spreadsheet import process is actually quite trivial. It's really back to back to back to back, parsing numbers and strings, occasionally formulae, that are inside cells in a spreadsheet. So what we do here basically is kind of an inside out locking. We essentially we drop the solar mutex before we spawn our threads. So reentrancy hazard starts to exist at this point in quite a nasty way. And then we spawn all of our threads to import each of these worksheets from different XML streams. And of course, we spin up other threads in the background to start parsing them and stuff. So it's really quite thread heavy, this piece. But the first thing we do in those threads is we take the solar mutex. We want to be safe, so that all of the existing quite complicated code to do all of the existing quite complicated stuff is protected in the same way that it used to be. So actually only one of those threads gets into that zone where it can actually start doing stuff. So that seems a total waste of time. But of course, when we get to our very inner loop there, the bit that's chewing most of the XML, we say, right, this is the bit that we think is safe. And we have a thing called the solar mutex releaser, which already exists and is there for yielding back to our main loop. And basically, we count the number of times the lock was held. We release it that many times. And we let these other threads get in while we're doing our inner loop and processing all of that data. So we essentially release the solar mutex around that performance critical piece that takes much of our import time. And we allow other threads to carry on holding the solar mutex and doing stuff that is, more risky. So that's slightly counterintuitive use of locking, and probably not very orthodox, but at least allowed us to rapidly thread XLSX importing. So it's really quite fast. So that's that. I'll look at the cool stuff just quickly, and then hopefully we've got some time for questions. So the first thing really to say is that threading is sufficiently hard that we don't allow it to be done by JavaScript programmers, for example. So JavaScript has kind of not allowed threading to occur, which is very sensible in some ways. But you can sort of achieve that by having workers and passing messages between them. So you can actually have multiple threads. But at the end of the day, you get messages in queues, and those messages arrive in an order that you can understand, define, debug, and hopefully test. And So then there is a very little bit of thread-safe code that produces this message passing between threads, and then otherwise life is quite simple. And this is at least one way that threading can be made reasonably easy to understand and comprehend. I think on the opposite end of the extreme of this, Java has this synchronized keyword, which basically, does atomic operations on random variables, or does a lock around individual methods on objects. And this is, to some degree, an absolute nightmare. It encourages hypergranular threading and creates endless threading problems. It's kind of the anti-pattern for how you should not do concurrency, I would argue. Anyhow, so what are the threads we have in col.la Online? So the first thing is to understand we have a thing called the socket poll. And the socket poll is to, is I guess the fundamental threading enabler in col.la Online. So it just sits there and it wraps a poll call, because it turns out that the kernel has, hey, similar problems to what we have. And the kernel gives you file descriptors. And if you want to know if something is happening on any of the file descriptors, is there more incoming data? Is the space to send stuff and so on? You essentially call the poll system call, or some more modern version of it. There are more modern versions for various corner cases. And so basically, actually VCL has something like that very much in the middle of it. So most of the time LibreOffice on the Linux system is stuck in a poll call. On Windows, it will probably be stuck in a wait for multiple objects call, which does a similar thing. And I think on Mac, it's probably inside the Mac magic as well. But yeah. So the poll sits there waiting for stuff. And then when things come in, it can process events and do stuff. So we have multiple of these polls. Some of them have poll at the end, some of them don't. But they're basically sitting there spinning one of these socket poll things. And the nice thing about a socket poll is it has an easy message passing interface on it. So you can say, add a callback to the socket poll, and that callback will be called not in your current thread, but in that thread over there, if that makes sense. The thread associated with the socket poll. So we have a number of these. So there's an accept poll. So accept poll is just sitting there waiting for people to connect to us at a TCP, very low level TCP level. So fielding incoming web requests for us. And then those goes over to this web server poll, which then does a whole load of web serving, right? But more than that, it upgrades WebSockets to, upgrades HTTP requests to WebSockets as and when we discover that it's a request for a WebSocket. So that manages those things. So it does all the file serving and, yeah, bits like that. Then we have a thing called the prisoner poll. So this is the guy that is sitting there talking to any of the child kit processes. So every time we load a document, we launch a kit process. Well, okay, the kit process is usually pre-launched. So we have one kit process per document. And that kit process then has a single, what's called Unix domain socket, or UDS. And that's a very high-speed networking connection. And so you end up with a file descriptor to a very fast channel to talk to that kit process. And it's just one of those. So all of the clients connecting to one document share that one socket. But either way, when we pre-fork those sit around and they make a connection to the prisoner poll, they say hello, and they're waiting for use, essentially. Now, async DNS is an interesting thing. This is, I guess, Quaylon's work. Perhaps he can tell us more about it in a bit. But the fundamental problem is that when you want to do a domain name lookup, there are basically no good asynchronous APIs defined for this that I'm aware of at all. So what's the problem with that? Well, the problem is that a DNS lookup can take between, millisecond and seconds. So, this is doing essentially a globally distributed database lookup on a name. And it's really not a good idea if, while we're handling web requests or whatever, we have to take a potentially 20-second delay to go see if this domain name looks up and where it directs to. So we have a magic thread that then has a queue of DNS lookups that can go and do this. Now, this is really a terrible implementation horror, but it's the reality of RC APIs, and there it is. But there's a queue of domain name lookups. The good news is that most people look up the same domain name again and again, and it's not really a big problem. But either way, you can you can ask to be given a callback when your DNS request is completed, and then you can go to sleep and carry on spinning the loop. So it blocks, but it doesn't block anyone else. So all of these socket poles have multiple things happening asynchronously on them. And how does that work? So say we read from a file descriptor, and that file descriptor is actually connected to a web browser at the other side of the world. So when we read from that file descriptor, if we did a blocking read, well, first of all, that wouldn't complete until either the connection closed or the browser sent something at that end, which would be really unfortunate. And so what we do is we set all of our file descriptors to own on block. So there's an option you can have when you create a socket, or you can actually update it after it's created, to say, actually, if there's nothing to read when I read on this file descriptor, I want you to return me an error. And that error is called E again, as in try again, better luck next time, you know? And luckily, poll, we can put all these sockets into the poll system call, and it will tell us, hey, that file descriptor has something worth reading on it. So we don't have to, ironically, we don't have to poll them all. We don't have to go through all of these file descriptors and read and check for an error. We can just look for the ones where we know something has really changed. So that's essentially how it all works. And so because of that, we can have lots and lots of different sockets, all in the same socket poll, work out which ones have things that need reading, which need writing, and process just those as we go. So col.la has its own socket poll, and that just basically manages other things and cleans up and does a little bit of accounting. Poco, it seems to have a new thread, a wait queue thread. I don't know what the wait queue is for, but maybe it does something useful. Possibly we could kill it. Aha, there we go. So PS tree minus PLT. Look at that. So this is a great command that then will show you the hierarchy of threads and their process IDs and so on, and their names for col.la if you happen to be running it. And then there's an admin thing. So it's thought that the admin console should probably be, somewhat separate from this. So the web server poll and the accept poll take things that go through, hand it over to the admin poll, and then the admin then manages, remote monitoring connections and Prometheus metrics and serving things like that. There's another thread, which is the remote font config thread. And I think that probably does what you might expect, managing fonts and so on. So those are the main threads in col.la. But in addition to that, we have some per document threads. So these guys are all around all the time, pretty much. So they're all sitting there waiting to do something useful. As we create a document, we have then a number of threads per document. And one of the design choices that we make is that each document would have then one thread in the document broker. And that is a beautiful thing because it means you can be sure that only one thing is happening at once. You don't need to take locks. You don't need to do anything inside that socket poll. As long as you're not talking to another socket poll, there's no need for any locking. So we can do arbitrarily complicated things in terms of callbacks and things between modules, and we can't deadlock and we can't screw things up. It's really important that col.la doesn't deadlock because it's really, that takes all of the documents down if it does so. So anyway, that document broker thread or zone then covers a whole load of code. There's the document broker, there's the client sessions, there's WAPI, WAPI handling. I think maybe WAPI handling happening inside that. And yeah, that's consuming events, then sucking them in from each of the browsers, talking down that domain socket to the kit process, and all is good. And single threaded effectively for each document. Now the forkit, interestingly, you've probably heard about the forkit and all the joys of memory sharing and zero copy, zero copy on write stuff that goes on inside the forkit. But the fundamental reason that we need a forkit is that as soon as you launch a thread, you can't fork. So I'll say that again. If you have a thread, actually, to be fair, I lie. You can fork if you have a thread. It's just really, really, really dangerous. So, for example, if you have two threads and one of them is allocating memory, and it's just asked for a particularly difficult to serve memory allocation, maybe a large chunk of memory that needs to be backed by pages, and it's stalled that thread. And meanwhile, the other thread in your process forks. What happens is that the new process doesn't end up with a copy of both of those threads. It only ends up with a copy of the whole memory space and the thread that forked. And so the consequence of that is that you now have a lock held on your memory allocator that was held by that other thread, and now you can't allocate memory anymore, which is kind of really bad, really bad. It makes it hard to make progress, you know. And so the whole job of the forkit is not just to do this copy on write management of memory and sharing of things, but also to have only one thread. That's a big part of its business. So you'll see in there's only one socket pole, there is only one thread, and we spend quite a lot of time shutting threads down. Actually, as an aside, for the background save thing, we have essentially the same problem, that in order to fork and do a background save, it's necessary to close down all of the threads that we mentioned below, take us down to just one thread, and ideally check that we have only one thread, and then spawn that background save process. And then potentially restart them if we need them to save. Good. So then we have the kit processes that come out of that, and they're allowed to have threads, of course. And so we have kit broker 1, which is basically doing this unipole, this fusing of two main loops. So this graunches together the socket pole loop and also the VCL main loop. So they become essentially the same thing. And then there are a few other threads there for parallelizing things like tile compression, which is a significant workload that we do, and also slideshow compression. So there's a little thread pool there that has often only about 4 threads, because that's kind of a nice sweet spot to accelerate tile compression, because it's kind of expensive. Less expensive with Z standard, but still expensive enough. So I think pretty much that's the overview of threading in col.la Online and LibreOffice. I think, you know, threading, yes, even people who are extremely experienced in this field, which is not really me, having written quite a lot of this code, screw this up routinely. And worse, the screw-ups are not found for often years of successful operation until the thing just falls in a heap. And, you know, there you are. It's very, very hard to reason about threads. It's hard enough to reason about single-threaded reentrancy if that's uncontrolled. It's reasonably hard to reason about event ordering problems where things happen in different orders. But when you start threading things, you know, you have all of these problems and more. The main problem being that it tends to be unreproducible what you've done. So, you know, like it failed once, but why and how? And of course, you know, benign failures like deadlocks and so on are extremely easy to at least find, but you know, they're relatively rare because they get fixed quickly. It's more like the memory corruptions or inconsistent state that really screw us over. So against that, obviously we need to thread to, well, first scale on larger machines, but also you know, just take advantage of all that spare hardware really. So if we use them carefully and sparingly, life is good. I would argue if we're introducing some magical new threading thing, I'd really like to be reviewing that code and have some other, you know, several people look at it who really know what they're doing. It's going to delay your code getting in. And I'd also want to know why we're threading it, as in, have we got a profile that shows this is a significant problem? We shouldn't be doing this casually. We should be doing it very, very seriously. Not before optimizing, you know, profiling, I guess. Never parallelized before. I meant profiling, it's not optimizing. As I mentioned with the Java serialized attribute and other things, locking granularity is really not your friend. I mean, code locking is something that even you know, underskilled persons like myself have a good chance of getting right. But trying to do hierarchies of locks and highly granular locking and each object its own lock usually is a total waste of time, doesn't increase parallelism in any meaningful way, and inevitably causes horrifying problems. So I think we've managed to avoid having many lock hierarchies and complicated locking scenarios in LibreOffice and in col.la Online, and that's a real feature. If you look in the Linux kernel, of course, you know, they have different scaling concerns. And so, you know, there's all kinds of clever tree hierarchies and data structures that you take locks as you walk down yeah, but we're kind of trying to avoid doing anything clever. As soon as you do clever things, you know, your life is filled with pain. So, yeah. And one of the ways, of course, that we try and minimize the risk here is by putting a very tight scope around what we're going to parallelize. So, I mean, the great example is image scaling. there's a whole load of code. There's a whole load of different ways you can enter the image scaling code from different places all around the place. But at that point, everything is relatively well controlled. We know the solar mutex is held. We know we own the memory. We can't re-enter. We have a well-defined, smallish set of code that is running as a child of that to do something. And yeah, so it's relatively easy to reason about and make sure that it is actually as safe as we can get it before we hit, go wild, go parallel. So I think that's about it. Message passing really does rock as a solution. And I think that's my talk. So questions, comments, feedback, heckling, stoning, let it all begin. Thank you. So I'm going to go and poll people then. Andrash, Dash, and Joao. Any thoughts, questions, comments? Do say yes or no in the chat or elsewhere.
No questions, but thanks for the talk. I need to go through it again, but yeah.
Terribly sorry. Fair enough. Jolly good. Laser Neil Torsten, I have.
No questions, just it's really interesting to start, now I've been here a little while, to sort of start to get a hang of the technical terms, as obviously not in a technical role, but you make it easier to understand.
Great. Well, I'm glad that helps. There are a lot of acronyms on there. I don't know. Educate me. Yes, no. Oh, good. We got some questions there. So Neil Torsten says no questions. Neil, I don't know if you're do put in the chat if you can't speak. Miklos, any thoughts, feedback?
Just one comment on one of the first slides about thread pools. I think one secondary usage of the thread pool is that in some cases, slide 3. So one other use case of the thread pool is that sometimes you want to do some action on, let's say, 1,000 items. And the naive way of that would be to create one thread for each and every of those items, and then you allocate too many resources on the operating system. So you don't want to do that, even if thread creation is fast. And then this thread pool has the nice property that you can push all of these jobs on the thread pool, and you just wait till it gets processed, and the thread pool takes care of using the optimal amount of threads to work through all of these larger amount of items. So that's a nice property now, I guess.
Great point, Miklos. Yeah, so underneath that pool then is, in theory, the optimal number of threads for that work. To be honest, as CPUs start to have this big little architecture and these low power cores and high power cores, it's not clear to me that we don't need to chop our work up into smaller bits, so the fast ones can finish quick and the slow ones don't. But honestly, I haven't looked too deeply into how work is managed across those to try and make sure that you're not, because traditionally we would chop our work up into roughly equal sized pieces if we could. So if you've got 4 threads, you chop it into quarters. If 2 of those threads are way slower than the other 2, though, potentially that doesn't win you anything. So I don't know. Anyone with good ideas on that should probably speak up. But yeah, in theory, the nice thing is then you can push lots of work into those queues. All of the message passing and success reporting and waiting is handled for you. And, we wrote it and it worked fine. And then we read it and there were bugs in it. And we ran it and it worked fine. And then it turned out there was another, I think we went through several iterations of getting the thread pool right. And you would think writing a thread pool would be really easy. Like it should be a computer science beginners something or other. But it turns out you can screw it up quite easily. So please do use a thread pool rather than writing your own. And even beware in that case. But yeah. So Attila, I don't know if you have thoughts or.
Thank you. No questions, but it was useful. Sometimes I find asserts where solar mutex just helps, and I was not really sure what they're doing exactly. But now I go.
Yes, it's always a little bit scary when a solar mutex helps. So just add one. I don't know. So we'll see. I think, Devansh, you have a question here. That's great. How can one decide when a process needs to be made async? So, yes. Right. So deadlock occurs when you have two threads and they take locks in different orders. So one takes lock A and then lock B, and the other one takes lock B and then lock A. And so each of them has half of the problem and they can't complete. Neither of them can be happy. So that's essentially deadlock. Relatively unusual in our code base, except that the Solar mutex really does make life quite unpleasant because it's hard to release. And, well, anyway, yes. Generally, avoiding thinking too much about this, just take the Solar mutex and be happy that you don't need to do much threading inside the LibreOffice core, is the general idea. Hopefully, over time, we can peel more and more away from the edge of the software, and life will be better. But, yeah. Thing is, computers, as I think Noel says, CPUs are so unbelievably blindingly fast that unless there's something really big that's happening that makes sense to split out, then there's really not much point in threading it. And there's only risk and maintenance aggro and learnability and understandability problems. So good to do that. In terms of deciding when something needs to be made async, inside Collabora Online, pretty much everything is async. If you're doing something blocking, you're doing something wrong. So that means, so if you're in the web server poll, say, for example, and you add a new endpoint, and that endpoint, is, well, tell me some question, and that question then does a synchronous database call, that could take a very long time. And during that time, nothing else can be done on that web server thread. So we can't serve new things. And so we basically try and hide APIs and wrap them. Anything that's synchronous shouldn't be easy to do. That's the hope. Of course, there are some things that are synchronous, like not a real problem, if that makes sense. Yeah. So though the APIs are synchronous, we kind of assume that those files are all local. They're not on some slow NFS system remotely that's going to take ages. It's not always a safe assumption, but it's a pretty good one. It is possible to do asynchronous file IO on some kinds of file. Yeah, I don't know how the kernel APIs work for that, but that's a pretty tricky thing to do. I rambled a lot. Did that help, Devansh? Or do you want to revisit the question? The pasta analogy. Yes. Salt like not like pasta. Yes. Fair enough. It's a good way. Yes, and don't eat too much salt, or you'll have a problem. Thanks, Noel. Balash, Byram, Quaylon, anything to add? Thoughts, questions? Quaylon, you must have some, useful insight that I've screwed up. Quaylon left at the critical moment. Gokai, Christian. Okay.
No questions, thank you.
Good to see you guys. I'm just trying to work through these people. Mohit, Michael Stahl, Noel.
No more comments from Noel.
Did you like the Java threading model? I'm sure there is much more that's worth saying about it, but I don't know what it is.
We can have a long conversation sometime.
I look forward to it. But if it's useful, it's worth. I mean, I don't want to be completely maligning other people here, but I do think the synchronized attribute is really not great, and it makes a not great model too easy to use in some ways. But yeah, that's just me.
Yeah, I just have a small detail. Just looking at the slide, the IPC thread doesn't have anything to do with UNO.
Doesn't it?
If you
fair enough. I should edit that out.
This accept parameter, then you get an URP acceptor thread, and once somebody connects, you will get 2 additional threads for the connection.
Oh, jolly good.
So it's even more threads.
Okay, so this is the remote command line argument thread, essentially. Yeah. I have.
Yes.